This is week 7, differential entropy, lecture notes in information theory. I'm Hikmet Kamberay, a professor at the Faculty of Engineering. An outline of the presentation for today includes differential entropy, AEP, joint and conditional differential entropy, relative entropy. First, I'll talk about the differential entropy. By definition, let x be a random variable with cumulative distribution function f of x equal to the probability of x being less equal to x. If f of x is continuous, the random variable is said to be continuous. Let f of x be the df over dx, which is the first derivative of f with respect to x. If the integral from minus infinite to plus infinite f of x dx it is equal to 1, then f of x is called probability density function for x. The set where f of x is greater than 0 is called the superset of x. By definition, the differential entropy h of x of a continuous random variable x with density f of x is defined as h of x equal to minus integral along the support set f of x log with base 2 of f of x dx. And this is equal to, based on the property in statistics, it is equal to the expectation value of this function minus log with base 2 of f of x. S is the support set of the random variable x, and the E denotes the expected value. Note that h of x depends on f of x. Therefore, it can also be written as h function of f. Beside h of f, it is defined if the integral exists on the equation above. As an example, we consider a random variable x distributed uniformly from 0 to a, such that its density it is equal to 1 over a, from 0 to a, and 0 elsewhere. The question is to find the differential entropy. And the answer is the following. From definition, we can write the differential entropy h of x as equal to minus the integral according to s, f of x, log with base 2 f of x dx. And this is equal to minus integral from 0 to a, 1 over a, log with base 2 of 1 over a dx. Because outside this interval, f of x is equal to 0. And we have assumed, even before, that 0 log with base 2 of 0, it is always equal to 0. Then if I integrate this one, you'll find out it is easy to show that it is log with base 2 of a bits. It is interesting to note that for a less than 1, log with base 2 of a, it is negative, and so the h of x becomes negative. Therefore, h of x, the differential entropy, can also be negative, and this is in contrast to Shannon entropy, h of x, where we said that is non-negative. The volume of the support set, it can be written, vol, it is equal to integral from 0 to a d of x. If integrated, gives simply a. Therefore, we can write that 2 to the power h of x, it is equal to 2 to the power log with base 2 of a, which is simply equal to a. Therefore, we can say that the volume of the support set, it is equal to 2 to the power h of x. Actually, this is not a coincidence. We'll give a proper meaning to this relation later on. And this could be not just in one-dimensional case, but could be also up to the n-dimensional case. A second example, we consider a random variable x with normal distribution. Let's say phi of x, it is equal to 1 over square root of 2 pi sigma square exponential of minus x squared over 2 sigma squared. And I want to find the differential entropy in knots. From definition, we get that h of x, it is equal to minus the integral along the support set S, f of x, Now, since I want it in knots, I don't use the log with base 2, but I use the ln of f of x dx. Then I replace the PDF, probability density function, phi of x. Then you'll get minus integral from minus infinity to plus infinity, 1 over square root of 2 pi sigma square exponential of minus sigma square 2 sigma square, which is simply phi of x, ln of 1 over square root of 2 pi sigma square exponential of minus x squared 2 sigma squared dx. Now this is equal to, the first term inside the integral is simply phi of x, the PDF. Then I calculate the ln of the expression which is inside it. Now, since it is product of two terms, 1 over square root of 2 pi sigma square, and the second term exponential of minus sigma square over x square over 2 sigma square, then ln of this product, it is equal to the ln of the first term plus ln of the second term. Now we start with ln of the first term, which is minus ln of square root of 2 pi sigma square. Then ln of the exponential, it is simply the argument inside the exponential. So it is minus x squared over 2 sigma squared. Then I have also the phi x outside the parentheses, and then in the integral. Now, if I integrate minus integral of minus infinity to plus infinity phi of x times minus x squared over 2 sigma squared, 1 over 2 sigma squared, I can bring it outside on here if you follow my cursor. Minus minus gives me a plus. Then I'll have the integral from minus infinity to plus infinity phi of x squared dx. Now this gives me simply the expectation value of the x squared plus. Now the second term will give me the minus minus gives me plus here, minus here with this minus here gives me plus here. Then I'll have ln of square root of 2 pi sigma squared, which gives me 1 over 2 ln of 2 pi sigma squared. Then this term can bring it outside the integral. Then I have the integral of minus infinity to plus infinity phi of x dx. But phi of x, it is a PDF. Then the integral of the PDF over all the supporting set gives you 1 based on the normalization condition. Then I simply get 1 over 2 ln of 2 pi sigma squared. Then I can continue further on the last line. The expected value of x squared, it is simply sigma squared. Then I'll have 1 over 2 sigma squared times sigma squared gives you 1 over 2. And I get the first term on the last expression, plus 1 over 2 ln of 2 pi sigma squared. Now what I can do, it is the first term, 1 over 2, can be seen as 1 over 2 times 1. But 1 can be written as ln of e. Then I'll have 1 over 2 for the first term times ln of e, plus 1 over 2 ln of 2 pi sigma squared. I can factorize 1 over 2, then I get ln of e plus ln of 2 pi sigma squared. This will give me the ln of product, which is ln of 2 pi e sigma squared, then 1 over 2 in front. And this is in knots. Now, let's go for the AEP, which is the following theorem. Let x1, x2, xn be a sequence of random variables drawn as independent, identical, distributed according to the density f of x. Then minus 1 over n log with base 2 of f of x1, x2, xn converges to expected value of minus log with base 2 of f of x, which is equal to differential entropy in probability. Now you could prove this one. For this, we can use the so-called law of the large numbers and the fact that the joint PDF can be written as the product of I from 1 to n of the marginals f of xi's, because x of i's are IID. Then from this, you can write that minus 1 over n log with base 2 of f of x1, x2, xn. It is equal to minus 1 over n sum of I from 1 to n log with base 2 of f of xi. Now this converges if n it is large to the expected value of minus log with base 2 of f of xi. But this is equal to differential entropy h of x, which is the proof of the theorem that I want. Now, consider the typical set. By definition, for epsilon greater than 0 and for every n, we can define the typical set A of epsilon n with respect to f of x as the following. This is the set of all n tuples x1, x2, xn from s to the power n, such that the absolute value of minus 1 over n log with base 2 of f x1, x2, xn minus h of x, it is less equal to some epsilon, where the joint PDF, it is equal to the product of I from 1 to n, f of xi. Now, another definition is the so-called the volume of the typical set A, where A, it is a subset of r to the power n, where r, it is the all real numbers. And this is defined as vol of A, it is equal to the integral according to the typical set A of d of x1, d of x2, up to d of xn product. Then we can have the so-called typical set theorem. The typical set A epsilon of n has the following properties. 1, the probability of obtaining A of epsilon n, it is greater than 1 minus epsilon for n sufficiently large. Second, volume of A epsilon n, it is less equal to 2 to the power n multiplied by h of x plus epsilon for every n. And the third property, the volume of A epsilon n, it is greater equal to 1 minus epsilon, 2 to the power n times h of x minus epsilon for n sufficiently large. Then another theorem says that the set A epsilon n is the smallest volume set with probability of A of epsilon n greater equal to 1 minus epsilon to the first order in the exponent. Now, from this theorem, we can note that it indicates that the volume of A epsilon n, it is approximately equal to 2 to the power n h of x, which is the volume of the smallest set that contains most of the probability. That is, in n-dimensional, side length could be written as the volume of A epsilon n to the power 1 over n, if we assume that cubicle-like shape equals side on all directions. Then this is equal to the 2 to the power n h of x to the power 1 over n. Then n cancels out, and you get 2 to the power h of x. This means that h of x, which is the differential entropy, it is log with base 2 of the side length. Now, this has some consequences. The low entropy implies that the random variable is confined to a small effective volume because corresponds to the small side length. And the high entropy implies that the random variable is confined to a large effective volume because corresponds to a large side length. Now, consider a quantization of a continuous random variable. Suppose that x is a continuous random variable with probability density function f of x. Now we divide x into the histogram bins, each of length delta constant. The position of the center of the histogram bin, it is defined as x of I, which is greater or equal to I times delta, and less equal to I plus 1 delta. And I takes the values from minus infinite, and so on, minus 2, minus 1, 0, 1, 2, and so on, plus infinite. And this, it is such that f of xi times delta, it is equal to the integral from I delta to I plus 1 delta f of x dx. Now let x with some index superscript delta be the quantized random variable of x. So this means that x delta, it is equal to xi. Then the probability mass function of the discrete random variable x delta, it is equal to the probability of x delta being equal to xi, and it is equal to p of I equal to the integral of I delta to the I plus 1 delta f of x dx. And this is simply equal to f of xi times delta. Then the Shannon entropy of the discrete random variable now x delta, it is equal to the minus sum of from minus infinite to plus infinite p of I log with base 2 of p of I. And this is equal to minus sum of minus infinite to plus infinite f of xi times delta log with base 2 f of xi times delta. Now log of base 2 of f of xi times delta, I can write it as the sum of logs, log with base 2 of f of xi plus log with base 2 of delta. Then I obtain two terms from the first sum. One, it is minus sum of from minus infinite to plus infinite f of xi log with base 2 of f of xi times delta, minus the sum of from minus f infinite to plus infinite f of xi times delta, or log with base 2 of delta. Now, if I take the limit when delta goes to 0, and assuming that f of x log with base 2 of f of x, it is integrable function, then we get that the Shannon entropy, it is equal to minus integral of f of x log with base 2 of f of x dx minus the integral of f of x dx log with base 2 of delta. Or, since the first term gives the differential entropy, then we get that the Shannon entropy, it is equal to the differential entropy minus log with base 2 of delta, because the integral f of x dx, it is equal to 1. So you can notice now that the density f of x of a continuous random variable x is a Riemann integrable. So whenever this is true, then the limit when delta goes to 0 of h of x delta plus log with base 2 of delta equals to the differential entropy. Therefore, the Shannon entropy h of x delta of n bit quantization, this means that when delta it is equal to 1 over 2n of a continuous random variable x is approximately equal to h of x plus n, which indicates that the number of bits required on average to describe x to n bits accuracy. Now consider this example. Suppose that x is a continuous random variable on 0, 1, and let delta be equal to 1 over 2 to the power n. Then I want to find the Shannon entropy h x delta. Then answer is the following. The differential entropy, it is equal to the h of x, it is equal to minus integral from 0 to 1 of 1 over 1 log with base 2 of 1 over 1 dx, and this is equal to 0, because log with base 2 of 1, it is equal to 0. Then the Shannon entropy of the discrete random variable xd, it is equal to h of x minus log with base 2 of delta. Now h of x is equal to 0, then you get delta it is equal to 1 over 2n, then you get 0 minus log with base 2 of 1 over 2 to the power n, which is equal to simply n bits. Therefore, n bits are required to describe the x to n bit accuracy. Now consider another example. Suppose that x is a continuous random variable on interval 0 to 1 over 8, and let delta be equal to 1 over 2 to the power n. Then I want to find the Shannon entropy h of x to the power delta. Then the differential entropy, it is equal to h of x equal to integral from 0 to 1 over 8 of 1 over 1 over 8 log with base 2 of 1 over 1 over 8 dx. Then this is simply minus 3. Then the Shannon entropy of the discrete random variable x to the power t, it is equal to h of x to the power t equal to h of x minus log with base 2 of delta. And this is equal to minus 3 minus log with base 2 of 1 over 2 to the power n. Or it is equal to simply n minus 3 bits. Therefore, n minus 3 bits are required to describe x to n bit accuracy. Next, I'll talk about the joint and the conditional differential entropy. By definition, the differential entropy of a sequence of continuous random variables x1, x2, xn with joint PDF f of x1, x2, xn is as follows. H of x1, x2, xn, it is equal to minus integral f of x to n log with base 2 f of x to the power n d of xn. It follows from the definition that the joint differential entropy, it is equal to the expected value of this function minus log with base 2 of fx to the power n. Now suppose a theorem, suppose that x1, x2, xn have a multivariate normal distribution with mean mu and covariance matrix K. Then the differential joint differential entropy h of x1, x2, xn, it is equal to 1 over 2 ln of 2 pi e to the power n, absolute value or determinant of the K covariance matrix in knots, where K, absolute value of K, it is the determinant of the covariance matrix K. Now the joint PDF can be written as f of x equal to x is a vector in bold letter, and then 1 over 2, 1 over square root of 2 pi all to the power n, the determinant of K to the power 1 over 2, then exponential of minus 1 over 2, x minus mu vector to the power, take it transpose, K inverse of the matrix, covariance matrix K minus 1, then x minus mu vector. Now the joint differential entropy is then calculated as the following, h of f, it is equal to minus integral of f of x, then I have minus 1 over 2 x minus mu to the power 2 transpose t, k minus 1 for the inverse of k, x minus mu minus ln of square root of 2 pi all to the power n, then determinant of k to the power 1 over 2. So the second, the brackets here, square brackets, are obtained by taking the ln of f of x. Then all integrated according to dx. Then this is equal to 1 over 2, the expected value of the sum of all ij's xi minus mu I ki of the ki elements, kij elements of the covariance matrix K, inverse of it, xj minus mu j plus 1 over 2 ln of 2 pi to the power n, determinant of K. And this is equal to 1 over 2, the expected value. I can write the sum in a different way, sum of all I and j's, xi minus mu I, then xj minus mu j, then the ij element of the inverse matrix K, plus 1 over 2 ln of 2 pi to the power n, determinant of K. Then this is equal to 1 over 2, sum of all. I use the fact that the expected value of the sum is used equal to the sum of the expectation value. This is the linearity property of the expectation. Then I get sum of all I and j's, expected value of xj minus mu j, xi minus mu I, kij inverse, plus 1 over 2 ln of 2 pi to the power n, determinant of k. This is equal to 1 over 2, sum of all I and j's, kji times kij, the inverse, plus 1 over 2 ln of 2 pi n, determinant of k. And this is equal to 1 over 2. Then I will have sum of all j's, the product k with its inverse, jj element, plus 1 over 2 ln of 2 pi to the power n, determinant of k. Then I can continue further. The k product of k with its inverse gives the diagonal matrix. Then I can write 1 over 2 sum of all j's, I, jj, plus 1 over 2 ln of 2 pi to the power n, determinant of k. This is equal to, now since the diagonal elements are 1, then I will have this sum, the first sum gives n over 2 plus 1 over 2 ln of 2 pi to the power n, determinant of k. Or can be written as, using n over 2, the first term here, as n over 2 times ln of e, all right? Or I could write it 1 over 2 ln of e to the power n, factorize 1 over 2, then I have ln of e to the power n plus ln of 2 pi n, determinant of k. Then I use the sum of ln, so will give equal to the ln of product. Then I get 1 over 2 ln of 2 pi e to the power n, determinant of k in knots. And this is what I wanted to prove. Now the definition of the condition differential entropy. By definition, the condition differential entropy, h of x given y, The continuous random variable x and y with joint PDF is as the following. H of x given y, it is equal to minus sum of integral of according to dx, integral dy, f of xy log with base 2 of f of x given y, where f of x given y, which is the conditional PDF, it is equal to the joint PDF f of x and y over f of y. Now it follows from the definition that h of x given y, it is equal to minus integral of dx, integral of dy f of x and y log with base 2 of f of x and y over f of y. Now this is equal to the log of the ratio. It is equal to the log of the difference of logs, log with base 2 of f of x and y minus log f base 2 of f of y. Then I obtain two terms. One, the first minus integral dx, integral dy f of xy log with base 2 of f of xy plus integral of dx, integral dy f of x and y log with base 2 of f of y. Then the first one gives me the joint differential entropy of x and y plus the second one, if I integrate according to the x random variable, f of x and y, then this will give me the margin with respect to y. Then I get integral of dy f of y log with base 2 of f of y. Then this is equal to the joint differential entropy minus the second term with minus in front give me the differential entropy of y random variable. Now I'm going to talk about the relative entropy. Now, by definition, the relative entropy or the Kullback-Leibler distance, d of f from g, between the PDFs f of x and g of x of a continuous random variable x is as the follows. d of f from g, it is equal to the integral f of x log with base 2 of f of x over g of x dx. From the definition, d of f from g is finite only if the support set f of x is contained in the support set of g of x. Furthermore, 0 log with base 2 of 0 over 0, it is equal to 0. Now we can define the so-called mutual information. By definition, the mutual information I of x and y between x and y, between the two continuous random variable x and y with joint density f of x and y, all right, it is as the follows. The mutual information between x and y is defined as the relative entropy between the joint PDF and the product of marginals f of x times f of y. And this is equal to the integral d of x, integral d of y, f of x and y, the joint PDF, log with base 2 of this ratio, f of x and y over product f of x times f of y. From the definition, we obtain this one, the mutual information between x and y, it is equal to the integral of dx, integral of dy, f of x and y log with base 2 of this ratio, f of x and y over f of x times f of y. Now we can take f of x and y over f of y, and this will give me the conditional PDF, f of x given y. Then we obtain the second line here. Now the log of base 2 of the ratio can be written as the difference between the log of f of x given y minus log with base 2 of f of x. Then on the third line, we obtain two terms. The first term is the integral d of x, integral d of y, f of x and y log with base 2 of f of x given y minus integral dx, integral dy, f of x and y log with base 2 of f of x. And this is equal to the first term gives me with minus in front the conditional differential entropy, h of x given y minus, and the second term, if I integrate according to the y, integral dy f of x and y will give me the margin with respect to x, and I'll obtain f of x log with base 2 f of x dx. Then the second term gives me simply the differential entropy of x random variable minus the conditional differential entropy of x given y. Now, similarly, we can express the mutual information between x and y as a continuous integral dx, integral dy, f of x and y log with base 2 of this ratio, f of x and y over f of x times f of y. And now I grouped differently. I take the f of x and y over f of x, then this will give me the conditional PDF of y given x, then af integral dx, integral dy, f of x and y, log with base 2 of f of y given x over f of y. Then log with base 2 of f of y given x over f of y can be written as the difference between the log with base 2 of f of y given x minus log with base 2 of f of y. Then I obtain integral dx, integral dy, f of x and y, log with base 2 of f of y given x, minus integral dx, integral dy, f of x and y, log with base 2 of f of y. Then the first term gives me with minus the differential condition differential entropy of y given x, minus on the second integral here, if I integrate along x, integral dx f of x and y will give me the margin with respect to y. Then I will have minus integral f of y log with base 2 f of y dy, which gives me the differential entropy with respect to y, then minus conditional differential entropy h of y given x. Now, knowing that the conditional entropy h of x given y is equal to the joint differential entropy x and y minus h of y, and h of y given x, it is equal to h of x and y minus h of x, then we can obtain the mutual information between x and y. It is equal to the sum of h of x plus h of y differential entropies minus joint differential entropy h of x and y. Note that the same property also for the discrete random variables. So this means that d, the relative entropy of f from G, it is non-negative, and also the mutual information between x and y, continuous random variable, it is non-negative. Now, we can find a relationship with a discrete case. For that one, we consider quantization of x and y in the range of their values. So we denote with chi the range of continuous random variable x, and the quantization delta x of chi is a set of disjoint intervals, let's say p of I, such that the union of p of i's will give me the old set chi. And this is denoted as x to some superscript delta x. Then the probability that x delta x it is equal to I, it is equal to the probability that x it is on the interval p of I, and this is equal to the integral p of I df of x. Similarly, for y, the quantization it is delta y of epsilon, and it is set of disjoint intervals qi such that union of qi will give me the epsilon, and it is denoted y with superscript delta y. Then the probability that y delta y is equal to I, it is equal to the probability that y it is on the qi interval, and this is equal to the integral according to the qi d of f of y. Then the mutual information, but on the discrete case random variables x delta x, y delta y, it is equal to the, based on the second lecture, it is the Shannon entropy of x delta x minus the conditional Shannon entropy h x delta x given y delta y. Then using the previous slide information, this Shannon entropy relates to h of x minus log with base 2 of delta x minus, then for the second one, I'll have conditional differential entropy of x given y minus log with base 2 of delta x. Then log with base 2 of delta x cancels out, then you get h of x minus h of x given y, but this is equal to the mutual information between the continuous random variable x and y. So you could notice from this one that with this quantization, the mutual information between the discrete random variables delta x, y delta y equals to the mutual information approximated to the mutual information between the continuous random variables corresponding one x and y. Then I could arrive in such a definition, which is called the equivalence. The mutual information between two continuous random variables, x and y, it is defined as follows. the mutual information between x and y is equal to the upper limit of delta x, delta y of the mutual information between the corresponding discrete random variables due to the quantization delta x, delta y, where the supremum is over all finite partitions delta x and delta y. That indicates that by continuously refining the partition delta x, delta y, so making smaller and smaller, we obtain a monotonically increasing sequence of I between the discrete random variable due to the quantization x delta x, y delta y, that converges to the mutual information between the continuous random variables x and y. And this is something as a practical implication if you want to calculate, to compute on the computer, the mutual information between the continuous random variables. Always we do a quantization and we calculate the Shannon mutual information between x and y, which are a result of the quantization. So this means that discrete case. Now, consider another example. I want to determine the mutual information between the correlated Gaussian random variables x and y with correlation coefficient rho. So let x and y be a Gaussian distribution, let's say n with mean value 0 and covariance matrix K, and then K is equal to, as this element, sigma square rho, sigma square rho, sigma square, sigma square. Then the h of x, it is equal to h of y, it is equal to 1 over 2 log with base 2 of 2 pi e sigma square. Then the joint differential entropy, it is 1 over 2 log with base 2 of 2 pi e square, a determinant of the covariance matrix K. Where the determinant now, based on this formula here, it is equal to the sigma to the 4, 1 minus rho square. Then if you replace, then we obtain the so-called mutual information between x and y. It's h of x plus h of y minus h of x and y. And this is equal to minus 1 over 2 log with base 2 of 1 minus rho square. So if rho it is equal to 0, then I get log with base 2 of 1 minus 0, or log with base 2 of 1, which is equal to 0. Then we say that x and y are uncorrelated in that case, and we can notice that also the mutual information is equal to 0. However, a comment on here, you should know that the independence, it is stronger, or dependence is stronger than correlation. So this means that the correlation here, it is a weaker measure of the dependence between two random variables than the mutual information. All right? So this is something that should be counted. All right? So you could have also, if rho it is equal to plus minus 1, then x and y are perfectly correlated. And in that case, the mutual information between x and y, it is infinite. So the one here, it is true. So whenever rho it is equal to 0, so whenever the correlation it is equal to 0, also the mutual information is equal to 0. It is only if x and y have a Gaussian distribution. If not, then this would not be true. So you could have cases if rho it is equal to 0, however, the mutual information is different from 0. But if the mutual information it is equal to 0 for any x and y random variables, then this automatically implies that rho it is equal to 0. So this would mean that the mutual information is a measure of not just the linear, but also non-linear correlations. It is a stronger measure of the dependence between, or not dependence between, two random variable x and y. So the first one holds if x and y have a Gaussian distribution. Now, a theorem related to the properties of the differential entropy, we have to show that the relative entropy of f from G, it is non-negative. And with equality, if and only if f it is equal to G, almost everywhere. It's a simple proof. We denote by x the supporting set of f. Then we start with minus the relative entropy of f from G. And this is equal to, based on definition, integral according to the supporting set, f log with base 2 of g over f dx. Then this is less equal to log with base 2 of the log with base 2 of integral according to the sum d. All right, here f g over f d of x, and for this one I've used the so-called Jensen's inequality. All right, this d here, it is the set, can be considered as a subset of S, where f it is different from 0. Right, f of x is different from 0. Ff cancels out, then you get equal to log with base 2, then integral according to x, g of x dx. And this is equal to, since integral of s g of x dx, it is equal to 1 because g of x, it is a PDF, then I get log with base 2 of 1, which is equal to 0. All right, so it is clear that if f it is equal to g, then d of f from g it is equal to 0. Now, a corollary, we have to show that the mutual information between x and y, it is non-negative, with equality if and only if x and y are independent. From the above theorem, all right, the mutual information, it is equal to the relative entropy of the between f, the joint PDF x and y, and the product f of x times f of y. And I want to show, since we just showed that differential entropy is non-negative, that this implies that also the mutual information is non-negative. It is clear that if x and y are independent, then we can say that f of x and y, the joint, can be written as product of two marginals. Then the relative entropy is equal to 0 based on definition, and so the mutual information is equal to 0. Now, another corollary, we have to show that the conditional differential entropy, h of x given y, it is less equal to h of x, with equality if and only if x and y are independent. Now, from the above theorem, the mutual information between x and y is equal to h of x minus h of x given y. And this is non-negative, right? Because the mutual information is non-negative, that this implies that h of x given y is less equal to h of x. It is clear that if x and y are independent, then the mutual information is equal to 0, and thus h of x given y, it is equal to h of x. Now, the chain rule of the differential entropy, we show that the joint differential entropy, h of x1, x2, xn, it is equal to the sum of I from 1 to n, h of xi given x1, x2, xi minus 1. Then, as a proof, we use the relationship that the joint PDF, can be written as product of I from 1 to n of the conditional PDFs, xi given x1, x2, xi minus 1. Then we get that the joint differential entropy, it is equal to minus integral of f of x log with base 2 of f of x dx. And this is equal to minus integral f of x log with base 2 of the product I from 1 to n, f of xi given x1, x2, xi minus 1 dx. And this is equal to minus integral f of x. Then log of the product can be written as sum of logs. So I can write it sum of I from 1 to n log with base 2 of f of xi given x1, x2, xi minus 1 dx. Then I can switch the integral with a sum, then I get minus sum of I from 1 to n, integral f of x log with base 2 of f of xi given x1, x2, xi minus 1 dx. And this is equal to minus sum of I from 1 to n, f of... Now, this integral here, it is dx1 dx vector, it is equal to dx1 times dx2 and so on dxn. Now, since the f of log with base 2 of f of xi given x1, x2, xi minus 1 does not depend on xi plus 1 and so on xn, then I can, what I can do, I can integrate f of x here, this f of x, from xi plus 1 to xn. If I integrate that, this will give me the marginal of f from x1, x2 to xi minus 1. Then I obtain the fifth line minus sum of I from 1 to n, integral f of x1, x2, xi minus 1, log with base 2 of the same thing, f of xi given x1 up to xi minus 1. Then I remove from the integration dxi plus 1 up to dxn. Then I'm left with dx1, dx2 up to dxi minus 1. Then the term inside the sum with minus in front give me the conditional differential entropy. Then I obtain sum of I from 1 to n, conditional differential entropy xi given x1, x2, xi minus 1. Now, another corollary show that the joint differential entropy, it is less equal to the sum of I from 1 to n, h of xi. Now, using the chain rule of the differential entropy, which says that the joint differential entropy, it is equal to the sum of I from 1 to n, conditional differential entropy, h of xi given x1, x2, xi minus 1. Now, using the conditional entropy inequality, then we obtain that conditional differential entropy of xi given x1, x2, xi minus 1, it is less equal to h of xi. Therefore, we obtain that the joint differential entropy it is less equal to the sum of I from 1 to n, h of xi. Now, this is the final slide. So in summary, you should know about the differential entropy. Starting with simple joint entropy, differential entropy of one random variable, and the joint differential entropy and conditional differential entropy. And you should also be able to calculate the differential entropy for simple examples, which are provided this. Then as references, you should look at Thomas and cover book Elements of Information Theory, but you could also look at my lecture notes, which is a compilation of the book, which is called An Introduction to Information Theory. And thank you for your attention. See you next time.